Hello, everyone. Welcome to this session on prime numbers, where we'll be mastering 700 level questions on primes. Let me begin by introducing myself. I am Shweta, and I am a quant expert at GMAT. I also have with me Atreya here today supporting the session. He will be responding to your comments and all. Whatever I will not be able to respond to, Atreya will take care of that. And that said, let me start with the session. And again, I'll start with an introduction to this session now that we're done with an introduction to who I am, who my partner here is today. So, the goals of the session are going to be to demonstrate how you can apply one unified approach properly throughout, and through that, be able to solve 700 level questions in under 2 minutes. So, my goal is to make you confident of solving these on your own without any help after the session. The flow of the session is going to be like this. This is very important for you to understand. We will start with some warm up questions to warm you up, to warm myself up. We will have a total of 4 questions here, which you will do on your own. You'll have 500 to 600 level questions. These are easy because we're just warming up. Once you're done with all 4 questions, then we'll discuss the solutions all at once. And through those solutions, we will be revising the concepts. So instead of me giving you theory, this is a concept, now apply it on a question, we will be learning, we will be seeing the application of these concepts on the very questions that you will have come from. Right after this concept revision, it'll be time for you to put yourself to practice. We will have a sprint 1, which will be 3 questions of now a higher level, a slightly higher level, 600 to 700 level now. This time, though, we will not do all 3 questions and then discuss. The pattern will be 1 question, 1 solution. So you solve a question, then we discuss it. Then you solve another one, we discuss it. In the process, we'll be discussing any faltering points that that question might have, which people usually falter at. So people mark a lot, why? Because they think this, and this is what you should not be thinking. All of those things we'll do. Right after sprint 1, we will move to sprint 2, which will now be a step higher. You will have 2 questions, 700 plus level. After this, again, in sprint 2, again, there'll be 1 question and 1 solution. That's how we'll be discussing it. Both these sprints will have their own feedback and takeaways after each sprint. So once we're done with sprint 1, we'll be talking about what is it that you really take away from those 3 questions and what you should remember when you move on to the next sprint. And of course, the feedback, how you performed and how you should be, what you should really be working on. Throughout this discussion, we will have faltering point analysis, as I said, where people usually falter so that you don't repeat those mistakes again. Now, this is the flow of the session. Let's get started with the warm up. We will be posting links in the chat box. Here are the instructions. Let me show you the instructions. So as I said, there'll be 4 questions. 500 to 600 level, easy questions. You will be given polls to put your answers. Refrain from posting your answers in the chat box. This is very important for you to understand. If you just say, write down the answer to something in the chat box, and somebody else who's solving it will just read your answer, it might influence that person. Think about yourself. Maybe you were leaning towards B, and then you see a comment that says D. You'd be like, maybe that guy is right. But actually, maybe you were right. You might just give up on your answer. We don't want to influence anybody else from our comments. So make this a rule. This will be a rule throughout the session. No comments here. You will be given links in the chat box. Atreya will be adding those links. We'll just click on them, choose your option, and come back here on the session. And as I said, we will solve these questions after you attempt them, after all 4 of them are done. Time to solve these will be 4 minutes. So 4 questions, 4 minutes, because these are easy. Believe me, we're being generous with the time here because it's the beginning. We're just warming up. I hope you're all set. The poll will be here. The link will be here in any moment. We will come back here for solutions. Let's get started. Atreya, waiting for the link. Meanwhile, everybody get your pens and pencils and papers out. You might need to write stuff. The link might be here any moment now. there's a slight lag between StreamYard and YouTube if you're watching on YouTube. So it happens because of that. Yes, the recording will be available. Yeah. Okay, we see. Let's start with the solution then. Let's start with the solutions. Here we go with solution number 1. So this was the question we had. Which of the following statements is or are true? Prime numbers are always odd. One is a prime number. Two consecutive numbers can never be prime. So just see all the terms that we see here. We see prime numbers mentioned. We see odd mentioned. We see one is a prime number. So that's a test we are on. And we see something about consecutive numbers. So there's quite a lot when you're dealing with such questions where you have to tell which of these statements is or are true. You have no idea how many of them are true. There could be just one correct statement. There could be two correct statements. So what you need to do in such cases is you need to analyze each statement individually. So instead of me analyzing every statement, we will first discuss the concepts behind this, because right now there may be people who are not very comfortable with what prime numbers are, what about even and odd, and how do the two ideas come together. So let's start with the very basic here. We'll start with the very definition here of what a prime number is. So here you go. A prime number is a positive integer that has exactly two different positive factors, 1 and itself. Now, positive integers are what? These are 1, 2, 3, 4, all the positive numbers, and they should have two different positive factors. What's a factor again? A factor is something by which when you divide a number, it's completely divisible. There'll be nothing left. So, for example, you think about the number 5. Then the number 5 is divisible By which all numbers? It's divisible by 1 and then straight by 5. There's no other number, there's no other factor. So 5 is a prime number. That's the idea. You just have to have two different positive factors. What happens if I don't have two different positive factors? What if I have, say, more than two factors? Well, then you get composite numbers. So this is what it says. More than two positive factors would make it a composite number. Now, here's an idea before I show you the examples here. Think about this. Every number in the world, any number, let me just take 10,000, it will always have two fixed factors. What are those two? 1 and itself. So if I'm talking about 10,000, then it's 1 and 10,000. So I always have two factors, except the number 1. That has just one factor. So any other number in the world, any other positive integer, I will always have two factors. So if I want to check whether it is composite or not, I really just have to see, is it more than two factors? Where I already know two factors of it, one in itself. So the moment I find the third factor, I'll be done. I'll just call it composite. For example, look at these now. 4, 6, 8, 9. So if I talk about 4, leave aside 1 and 4 itself. You already have two factors. Now think about one more factor. What's another factor that it has? You have the number 2. In fact, every even number in the world will have 2 as an extra factor. So these are composite. 6 again, leave aside 1 and 6. You already have two of them. Another one, 2 again, or 3. You could have looked at any. So this is what a composite number is. So these are the two types that we've talked about, prime and composite. Prime will have two different positive factors, only two. Composite will have more than two. Now you might be wondering, you're either saying 2 or more than 2. What happens if it's less than 2? What happens if it's one factor? Well, what is that number? I talked about it briefly. That is the number 1. 1 is neither prime nor composite. For the same reason, you just saw the definition. It's not prime because it doesn't have two factors. It's not composite because it doesn't have more than two factors. So 1 has only one factor. So this is why I'm talking about 1, and this is the difference that 1 has. And why am I really talking about 1? Because if you go back to the definition, it says it's a positive integer that has two different positive factors, and positive integers start with the number 1. So it was required that we discuss every positive integer in the world. Now, here are some examples of prime numbers. Again, you can check any of them. They'll all have just two factors, 1 and itself. So 11, for example, it just has 1 and itself. Now look closely at the very first prime number, 2. Do you see a difference between this 2 and the rest of the prime numbers that I have in the list? I hope you do. 2 is even, while all the others are odd. Now, at this stage, I'm going to make a statement that 2 is the only even prime number. How am I so sure? I can't see all the prime numbers here. I'm sure because any other even number in the world, as I said, any other even positive integer will have 2 as a factor other than 1 and itself. So the moment I have 3 guaranteed factors, it is composite. It can never be prime. And that is why 2 is the only even prime number. Another little thing we'll observe here is these two numbers, 2 and 3. So if you look at the list of prime numbers that I've written, in this list, 2 and 3 are the only two numbers that are consecutive numbers. What is consecutive? Consecutive just means one after the other. So 2, 3, 6, 7, 21, 22, these are consecutive numbers. In my list of prime numbers that I see till here, these are the only two that are consecutive, and both of them are prime. Now here's another statement I'll make. 2 and 3 are the only consecutive numbers that are prime. There is no other pair of consecutive numbers that can both be prime. That means there can never be just a difference of 1 between two prime numbers. The gap will always be more than 1. So remember this. This is a very important point. Now here I want to contrast this with something, consecutive prime numbers. Just be very careful. All the prime numbers that I've written here, they are prime numbers one after the next, one after the other. So after 2, the next prime number is 3. After 3, next prime number is 5, then 7. So these are consecutive. Why? Because they are one after the other prime numbers. There's a difference between the two things. When I was talking about 2 and 3, they were consecutive numbers that were prime. But when I'm talking about 5 and 7, they are prime numbers that are consecutive. I hope you see the difference very clearly between these two. These are just words written here and there. You're still using the same words, consecutive and prime, but it makes a lot of difference when you put everything into context. Okay. Now that we have talked about all of this, let's see the statements one by one. What does the first statement say again? First statement says prime numbers are always odd. You now know, we've seen the examples here. 2 is an even prime number. So the first statement is incorrect. Second statement, 1 is a prime number. Well, we talked about that again. 1 is neither prime nor composite. Second statement is wrong again. Third, 2 consecutive numbers can never be prime. That's also false. We saw 2 and 3. They were consecutive numbers that were both prime. So for this question, these were the options we had. And since none of the statements here is true, we mark option A. I hope you all got this correct. This was the very basic of the concept of prime numbers and even odd numbers together. I am expecting some results on the comment box so that I can see the accuracy on this one. Next up, question number 2. Let's all go to question number 2 together. I hope this is clear to everyone. This was the question: how many prime factors does 4004 have? Prime factors. Now, I hope you understand why we even talk about this. Prime factors of a number. Think about this as just how your body is made up of cells. Cells are the building blocks of the human body. Similarly, every number is made up of prime numbers. It's the building blocks of a number. So I want to find those building blocks for the number 4004. Let's talk about this a little more before I come to 4004. Let's just think about the concept behind this. So suppose you have any positive integer, say k. So it's just a random thing. Then I can express it in this form. Look at this very carefully. It might look intimidating, but it's super simple. P1, P2, P3, these are all prime numbers, the building blocks. And M, N, R that you see here are the powers on these prime numbers. So what this means is, I have a building block, say I have a red blood cell and I have 100 of those. Then I have white blood cells and I have 25 of those. So it's basically that number. How many of a certain prime number do I have in my build-up? So this is what the powers are. Now here, as this says here, P1, P2, P3 are prime numbers, and M and R are non-negative integers. This is again a common mistake that people make. They think that the moment non-negative is mentioned, it means positive, but it does not. Non-negative means not negative. So something which is not negative does not have to be positive. It can also be 0. So it's a common miss. As I said, we'll constantly talk about faltering points. This is one big faltering point. Never miss 0 here. Now, why is it really non-negative and when is it positive? How does it make sense to have 0 as a power? Well, M and R are going to be positive every time, except when you're talking about the number 1. Why? Because you want to break 1 down into a product of prime numbers, is its prime factors. But one poor guy had no prime factors. It was alone. 1 was its own factor. So the only way I can write it in the form of a prime factorization will have to be if I say 1 is equal to 2 to the power 0. Anything to the power 0 is 1. So that's the only way. All other cases, if you're talking about prime factorization, the power should be positive. Look at this example here. So 4, I want to break 4 down into prime factors. So it's 2 times 2. So it's 2 squared. 8, 2 times 2 times 2. So this is 2 cubed. This is prime factorization, simple. I found what was my 8 made up of. And when you answer that question, you have to answer that in terms of prime factors of the number. Let's take more numbers. So 6. 6 is made up of a 2 and a 3. 2 times 3 is 6. 12. 12 is what? 2 times 2, 4. 4 times 3, 12. This is how you get the prime factorization. I used the term, this entire process that you do when you express a number as a product of its prime factors, we call it prime factorization. Everything fits, right? Factors, prime factors, expressing it, prime factorization. This process gives you all the prime factors that a number can have. So here in our question, we had 4004, right? So we really have to prime factorize. We have to prime factor 4004. We have to see what is it made up of. Now, when you think about these prime factors, the first thing that should come to your mind is this is an even number. 4004 ends with a 4. It's an even number. It definitely has 2 as a factor. So then you'll take that 2 aside. And what will you be left with? Well, you'll be left with a 2002, which is again even. Then you do another 2. So I hope you know the process that we follow for prime factorization. And this is what you will get: 2, 2, 7, 11, 13. So since 2 comes twice, you can write it in a more compact form as 2 squared. This is the prime factorization of 4004. Now the question is again, how many prime factors does this have? Now you might think here, do I count the two twos separately, or is that one prime factor? Well, when you're counting them, the correct answer here is 4. You will not count the twos twice. It's like, what kind of cells are there in your body? You won't say red blood cells and red blood cells twice. You just count them once. So every distinct prime factor will count towards a new prime factor. So how many do I have? I have 4. But I have two twos. That's a different thing. But how many prime factors? That is 4. So I hope this question again is clear to everybody. We will now move to question number 3. Just see how we're steadily building the concepts. The first one just gave you the definition, what prime numbers are, what prime numbers are not, what composite numbers are. And here it's one step further, taking any other number, and getting it in terms of its prime factors. Question 3 was this. Okay, I just got some very interesting data. Just 26% of the people got the second question correct. So there were a lot of mistakes, therefore. Maybe there is a lack of understanding in how prime factors work. So I hope then all the other 74% of you are now confident about this. Now, moving to question 3, which of the following statements could be true? Now, this is again a very important word. There are some situations where they say what must be true. Sometimes they say what could be true. So when they say must be true, you choose a statement if it's always true. No matter what happens, it's always true. Could be true, on the other hand, it can be true in some situations, it cannot be true in other situations. You will mark that right. So here I will just see the pattern. I'll see what kind of statements I have, because I will have to analyze every statement. This says n has 2 prime factors, then 3n has 2 prime factors. Okay, so we are multiplying something with n and we want to see what happens to the prime factors. Second statement, we are multiplying something and we're also raising n to the power 2. Okay, same thing is happening in the third one. The power is greater now. So essentially the idea here in this question is to see what happens to the prime factors of a number if you multiply something to it, or what happens to the prime factors of a number if you raise it to a certain power. So that's the idea that we'll be working on here. Let's see. So here again, we're starting with the prime factorization of a number. There's a number k, and this is the prime factorization. You know the drill. We just talked about this. What I'll do now is I will raise it to a certain power. So this is k to the power a here. How do you do that? You should know the exponent law, that if you have, say, 2 to the power 3 and the whole thing raised to another 2. Let me write that down. So I have 2 cubed and the whole thing another square. So the rule here is that the powers get multiplied. You get 3 times 2, 6. So that is the same idea we're using here. If the original power here was m, then because I raised it to another power of k, m and a got multiplied and they became am. So the same thing happened for the other powers as well. So now this is k to the power a. We started with k, we started with one integer k, and now we've raised it to a power. Observe something now. The prime numbers, the prime factors are still the same. P1, P2, P3. The only thing that changed was what? It was the power in each of these. So I can conclude something here, that k to the power a has the same prime factors as k. But there's one small thing you have to be careful about here. K to the power a should still be an integer. I mean, the power that you raise it to should not make it anything else. For example, if k was 2 and then you do the square root of 2, so you raised it to the power half, then you can't do that, because square root of 2 will not even have any prime factors. So you have to make sure both of them are integers. Only then can you talk about prime factors. So here are some examples again. We had k is 2. So when I raise it to the second power and it becomes k squared, it is what? 2 squared. But the prime factor didn't change, right? It's still 2, only the power changed. Another one, you have this k now, which has 3 prime factors, 2, 3, and 5, and then you raise k to the fifth power. So you see all the original powers here, they just got multiplied. These were 1 and 1, if you could see nothing. They've now gotten multiplied by 5, but your prime factors have still not changed. So this is idea number 1. The powers will not change the prime factors. The other thing that we had in our statements was, what if you just multiply? For example, for statement number 1, there was no power there that we were dealing with. So let's talk about that as well. So here you have ak. So I'm multiplying a with k. So as a result, this a comes here on the side along with the prime factorization. So I can still see p1, p2, p3, the old prime factors, but what is this a? What do I do about this? I don't know whether a has the same prime factors as the ones I already had, or does a give me something new? So everything depends on what this a is. Here what I'm saying is ak may or may not have the same prime factors as k. Now this will become more clear when I give you an example. So here's example 1. So k is 2, and then I say 2k. So the value of my a is 2. You see how 2 did not give you any new prime factor. You still have 2 squared. So it's the same prime factors. But on the other hand, if I have k as 2 squared times 3 times 5, and then I multiply it with 7, then I'm giving a new prime factor to this product. 7 was not there earlier. So k had 3 prime factors, 2, 3, 5. But 7k has 4 prime factors, 2, 3, 5, and 7. So you have different prime factors now. I hope you understand how multiplying something may or may not change the prime factors that a certain number has. Now, here are the options we have. I'm sorry about the annotation on the options. Let's analyze these now statements. The first one, n has 2 prime factors, then 3n also has 2 prime factors. Is it possible? We just saw, when does it happen that your prime factors still stay the same? Look at this here. It can happen if n had the same prime factors. I mean, if 3 was already a prime factor of n, then nothing is going to change. So this statement can be true. Next, if n has 2 prime factors, then 5n squared has 3 prime factors. Okay, let's break this down into 2 pieces. So first of all, n has 2, so n squared will also have 2. How am I so sure? I saw that here on the right hand side. The powers will not change the prime factors. But then the 5. Well, I can see that the statement wants me to go from 2 to 3. So the statement wants me to see, is it possible that the number of prime factors increases by 1? Well, you'll see again, because of this second type here, it is possible that you get new prime factors. And how is that going to happen? That is going to happen if 5 that you've now multiplied with n squared was not already a prime factor of n squared. So of n. So it's a new prime number that you're giving it. So earlier you just had 2. Now you give it 5 also. It becomes 3. This again is possible. Next, if n has 2 prime factors, then 7n to the power 7 has 4 prime factors. Well, this is very similar to statement number 2. If n had 2, first of all, n to the power 7 will also have 2. Now, even if 7 was not already a part of n, you add that 7, you can still get to 3 prime factors. You can never get to 4 prime factors. So this statement here is impossible, and the answer is 1 and 2 only. These are the only ones that could be true. There can be situations where they are true. Now, this was question number 3. I can read comments and people are saying Mayank has answered 1 and 2, both could be true. Kirtana says she considered n equal to 6 and solved. So took an example. 47% of you people got this correct. So I hope the other 53% now is confident about this. Give us some more responses here. Tell us if your confidence is increasing, if you're learning new stuff here. I'll meanwhile move to the solution for question number 4. This is for, we had n equal to 900. So we're given a number 900 and we're saying which of the following statements about n must be true. Just see the contrast. I talked about this in the previous question. Could be and must be, the difference between those things. Must be true. Now I'm going to only select a statement that is definitely true. No matter what happens, there's not a situation where it can go wrong. So statement number 1 says total number of factors of n, then odd factors, then even factors. Okay, we don't know about this yet. We know how to talk about prime factors, but what is this? I don't see the word prime. So there is a difference. Prime factors are the building blocks. I talked about that. But factors need not be prime. They're just other numbers that you can divide by. So how do you get factors? Before I start with this, just take this as a task. You have the number 10. Now, if you prime factorize 10, it's 2 times 5, right? So you have 2 prime factors, just 2 and 5. But if I say, tell me all the factors of 10, then the factors are 1, 2, 5, 10. I had to count. Will I always have to count? What about 900? Will I see what all it is divisible by? 1, 2, 3, 4, 5. That'll go on for a while. So there has to be a better way. There has to be a way I can get to the total number of factors without having to count them like this. 10 was a small number. We can't do that. That is what we're going to learn here in this solution. So that's the next concept you're learning. Again, everything begins with the prime factorization, even though you don't want the prime factors themselves, but it starts here. So here's the prime factorization. Again, P1, P2, P3 are prime numbers, and M and R are non-negative integers. Now, the total factors of this are going to be M plus 1 times N plus 1 times R plus 1. What is this? Where is this coming from? Just observe this carefully. M comes from here, the power on the first prime number. You add a 1 to it. Second, then you take the next power, the power on the next prime factor, you add 1 to it. And so on you do for as many distinct prime factors as you have. You keep counting them. And once you increase them by 1, you just multiply all of that. The product is going to give you the total number of factors. Again, before going to 900, I want to talk about the 10 that we already had. So what's the prime factorization of 10? This is 2 times 5. So the powers, I'm sorry about the handwriting. So the prime factorization is 2 times 5. The powers here are what? It's 1 and 1. Now, what did I tell the rule was? The rule was to add 1 to the powers. So they'll both become 2 and 2. Multiply them. 2 times 2, 4. And I did count 4. 1, 2, 5, 10. Simple. Now apply this to this big number that you have here, 900. You prime factorize it. It is 2 squared, 3 squared, and 5 squared. We should not have the dots here. The prime factorization ends here. Now you just add 1 to each power. They become 3, 3, 3. Multiply them all, and 27 is your answer. You're going to have 27 factors for 900. However, if I'd asked just the prime factors of 900, you would have said 2, 3, 5, just 3 prime factors. Look at the difference between the two. Prime factors are just the prime ones. Factors can be anything, just about anything. So this is exactly what we had in statement 1. Okay, so we already found one statement which is always true. Let's move on and see what can help us get to statements 2 and 3. So this is again what we had from the previous slide. We have 900. Now it says total number of odd factors. So a factor has to be odd. That means what? It should not have a 2 in it. 2 should not be a factor. So if you look at all the factors that 900 has, all the prime factors it has a 2, a 3, and a 5. Essentially, it's the 2 that makes things positive, right? And I don't want that because I want odd factors. I'll just cross out the 2. So ignore this part and focus only on the other part, the prime numbers that we have otherwise. So 3 squared times 5 squared. Now with this, if I just work on this small number, I'll again apply the same formula, add 1 to the powers, they become 3 and 3, multiply them 9 factors. So you're going to have 9 odd factors, which is exactly what statement number 2 says here. This is true. Finally, total number of even factors. We're almost done with this now. If you know the total factors, you know the odd factors, just subtract odd from total. You'll get the even factors. So 27 minus 9 is 18, and your last statement is correct as well. Here were your options, and E is the answer. Let's see how many people got this correct. Rahul asks, any way to get even factors except total minus odd? There is a way, but what you'll have to do then is, essentially, when you take the power, when you add 1 to it, you really give it this possibility that the power that you take can include 0 as well. So you will have 0, 1, 2. That is how a power of 2 becomes 3. But if you want to make sure that the 2 is always a part of this thing, then you will never include 0 as a power, because then 2 to the power 0 will make it 1. So what you do is you will take the power 2 only from there. You will not add 1 to it. Then it becomes 2. For the other guys, you still add 1, because you still include 0 and 0. So it'll be 2 times 3, which is also 18. I hope you understood this, but this method here is more direct. You will not have to be very careful every time you work on it. I'm glad you got it, Rahul. So this was all about our 4 warm-up questions. I hope everybody got a lot of concepts cleared here. After this warm-up session, before we move to the sprint, let me just tell you about some upcoming sessions we have. This Saturday, 6th February, you have a GMAT RC webinar, Reading Comprehension. You will learn a new approach to RC. I know a lot of people struggle with this. How do I manage the time? How do I get the questions right? Learn all of that. Learn how to solve 700 level questions in 6 to 8 minutes. Shraddha and Harshvardhan, our verbal experts, are going to take the session. You have the link to register there on the chat box. Just click on that and register. Another one coming up is an algebra webinar by Atreya, our co-host for today. You will be learning algebra questions there, learning how to solve tough questions in under 2 minutes. So the link for registration is again in the chat box. Let's come back to where we were. Before that, we have one more thing. This is very interesting. Now, think about this. You are somebody who's currently at a 460 level, and your target score is 740. But you don't know what to do. You don't know how to go from 460 to 740. What should you work on? How would you know what your weak areas are? How to move on? So for that, you can book a free call with our strategy experts. They will analyze your performance. They'll see what your target is, and they'll ask you a lot of questions. You'll have this personal time with them, in which they will be able to guide you best. They'll tell you what you should focus on. Remember, it's limited slots, and they're given on first come first serve basis. The link for registration is again in the chat box. Now we're coming back to the session. As I said, the next part of the session flow was a sprint, where now you have to apply everything you learned in the warm-up section on this sprint. So the pattern this time is going to be 1 question, 1 solution, 1 question, 1 solution. The poll, again, you will be given a poll. The link for that will come in the chat box. Here are the instructions. First, you'll have 3 questions, 600 to 700. Remember, warm-up was 5 to 600. This is 6 to 700. And you will have to poll your answers in the link that you get. Nothing in the chat box, remember. Let's not influence anybody else's answers. And time to solve each question should be approximately 2 minutes. Good luck. I am showing the first question here, but you're marking it there on the poll. Let's get started. Okay, let's come back to this. Let's start. I hope you had a good time doing this one. Here's our question. Let's come back. Okay, so this was the question you all solved. We have a 56% accuracy for this, which is good. 44% of you still got this wrong. Let's hope we get everybody together on the same page after this, after our discussion. So the solution again, okay, so there's a lot of information. Q is the square of an odd positive integer. 8q to the power 8 has four distinct prime factors. How many prime factors does square root of q have? There's quite a lot. So here, before I start, I'll give you one tip. Never be overwhelmed by how much information a question has. Just take it bit by bit. Analyze every piece in it, work on it mathematically, infer everything you can, understand everything you can from this, and then move on. Towards the end, by the time you read the whole question and you have everything organized, you'll never have a hard time figuring out what to do. Here now, if I start reading this, q is the square of an odd positive integer, so that something happens. I want prime factors of square root of q. I have to keep that in mind. What is it that I'm looking for? Because that will direct how I work on it. Now, prime factors of square root of q, this is what I want. Can I just say this is equal to prime factors of q? Given this that you see on the screen, this is where we're coming from. We already know that k and k to the power a will have the same prime factors. Remember there, I said there was one condition that k and k to the power a should both be integers. Now here, if I want to say that prime factors of q are equal to prime factors of square root of q, then I have to make sure both of them are integers, right? This is an important point. If you miss this, you will get the wrong answer. So we have to make sure that we consider the fact that square root of q is an integer. So first of all, the question should give us some information that tells us this. Otherwise, we don't know what to do. Otherwise, we cannot connect square root of q with q. And if square root of q is not even an integer, then they will never ask us about prime factors because they don't have prime factors. So maybe there'll be an option you cannot determine that, or there are no prime factors or something like that. Now here though, let's see if the question tells us any such information. You have q is the square of an odd positive integer. So let me take that integer to be n. You see that in red here. So if q is the square of n, then this is how I can write it. Q is n squared. What is square root of q then? Well, square root of q then is equal to n. This is how it works, right? If 100 is the square of 10, then 10 is the square root of 100. This is how they're connected. So square root of q is n, which you already know is an integer. This n is an odd positive integer. So now that I know square root of q is an integer, I can use the result, this one in red, that prime factors of root q and prime factors of q are equal. And if they're equal, then all I have to do is I just have to find the prime factors of q. Remember, that is what my question has now become. Next piece of information, 8 times q to the power 8 has 4 distinct prime factors. Doesn't look very neat, very easy to process right now. Let's see what we can do with this. So we're talking about 4 prime factors that this has, and I can see the number 8 in it, which is not a prime number. So what I'll do is, I don't know what q is, but I can at least talk about the prime factors that 8 has. So I can write it in this way. 2 cubed times q to the power 8 has 4 prime factors. Now, if this has 4 prime factors, I can again use this result that I know. K to the power a and k have the same prime factors. So 2 cubed is the same as just 2. Q to the power 8 will have the same prime factors as just q. So simplifying that, this is what I have. 2 to the power 3 becomes 2, q to the power 8 becomes q. Look at how simple this is from where I started. I started with 8 times q to the power 8, and now I'm at just 2q. So 2q has 4 prime factors. So there's 2, and there are some prime factors that q is giving us. I really don't know yet whether 2 itself is also a prime factor of q. I have no idea about that yet. But maybe the question tells me something like that. Let's see. So we know that it's an odd positive integer n. So n is odd. And q is n squared. So if q is the square of an odd number, then q is odd. check anything. So 1 times 1, 11 times 11, or 19 times 19. Whenever you multiply an odd number with itself, it is going to be odd. What do I do with this now? If q is odd, it does not have 2 as a factor. What that means is, if I was talking about 2q, then 2 was separate and the prime factors of q were separate. So I can really write them like this. Look here. I have 2 and the prime factors of q. Together, we have 4 factors. 2 is not a part of q itself. That means the prime factors of q are just 3. The other 3, basically. How do you get 4 otherwise? So if q has 3 prime factors, then square root of q has 3 prime factors based on where we started, remember. We had already simplified it to this stage. Your answer is 3. Let's get it in the options. C is the answer. What is the accuracy for this one? Yeah, we talked about it. 56% of you. All right. I hope the other 44% is now clear with this. Get in some comments. Okay, we see that we are. Meanwhile, I'll move to solution for, we'll move to question number 2 together. You will have the link there in the chat box. Let's start. Okay. I hope we're all done. We have our solutions in the poll. Let's see the results and let's start discussing this one. Okay, what all do we have again? We have a positive integer x. Okay, before I read that, 71% of you got this correct. You see how the accuracy is gradually increasing? This is very interesting. So a positive integer x has 3 prime factors and 8 total factors. Remember, you remember the difference between them? Factors and prime factors are different. Factors, in fact, are formed using your prime factors. Prime factors are just the building blocks. Question is, how many factors does x to the power n have? So I have something about x. I know how many prime factors it has. I know how many factors it has. And my question is about x to the power n. Let's see this. Okay, first piece of information again. I will follow the thing I said, go piece by piece, bit by bit, and let's understand everything. So 3 prime factors. Okay, how can I use this? I can express x in this form now. The 3 prime factors that I had can be P1, P2, P3 with their respective powers of A, B, and C. And it also tells me that it has 8 total factors. Okay, now I know something about total factors. I know how we calculate total factors, right? You add 1 to the powers and then you multiply everything. Here's the result. So if this is the prime factorization I have, then the total factors I will get by doing A plus 1 times p plus 1 times c plus 1. So in my case, this product turns out to be 8. So this is the first thing I have. Now see, this is super simple. You have three numbers. Now that we've broken it down to this stage, you have three numbers which you multiply to get 8. What can those three numbers be? Well, the three numbers can be 2, 2, and 2. In case you're wondering why they cannot be 8, 1, and 1, you're not allowed to have 1 because if, say, c plus 1 is 1, then that means C is 0. And if C is 0, you will just lose this third prime factor, P3. But you know you have three prime factors. So none of these here can be 0. A, B, C cannot be 0, which means none of these three can be 1. The only way you can break this up is 2, 2, 2. And through this, you get the values of A, B, C as 1, 1, and 1. So X really is this. This is the prime factorization of X. And if this is X, what is X to the power N? This is X to the power N. Again, this is the same law of exponents that we talked about. The powers just get multiplied. Now 1 times N is just N. And now I want to know how many factors this has. Remember, if this was just how many prime factors this has, we would have been done without doing anything. If X had 3 prime factors, then X to the power N also has 3 prime factors. We're doing all of this because we want factors, not just prime factors. So what do we do again? Same method, add 1 to the powers, multiply them. N plus 1 cubed is your answer. In the options, that is option D. I hope everybody is super clear about this second question. We have just one more question to go in the first sprint, and then a small feedback and takeaway on all of this. Let's move to the third question. The link will be here, and this is the question. Nobody comments here. Let's start. All right, we have the answers here. Let's come and discuss this together. This was your question. We will again use the same approach I talk about, piece by piece, bit by bit. X is, and again, before that, we have 56% accuracy this time. So the accuracy is lower. Maybe this time there was something difficult that you found in this one. Let's hope we clear all of that confusion through the solution. So, first thing, what is it? We have k is a factor of positive integer x, and x has a total of 8 factors. So really the first thing is all unknowns. I don't know what k is, I don't know what x is, so how do I even express anything mathematically? The very first mathematical information I get is this about x having 8 factors. So let's start working with this. You know, 8 factors or total factors. How do you get total factors? It is this. If you have this as your prime factorization, then you add 1 to the powers, you multiply. That's the same thing we have here. This time, this product should come out to be 8. It's similar to how you have it in the previous question. But the possibilities this time are not just 2, 2, 2, because there we had this restriction that we had to have 3 prime factors. This time, though, we'll see all possibilities that there are. These are 3 possibilities that you have for getting the product 8. Now, each of these will have a different possible prime factorization from which it will come. So if you look at the first one, 2 times 2 times 2, the possible prime factorization will be this. How? The powers are just 1 on these because there are no powers, it's 1. And then you will have increased each of them by 1. 1 plus 1 is 2. And that is why all of them became 2. So this is prime factorization number 1. Next, when can this one happen? Well, this can happen if you have a prime factorization like this. You have just one prime factor with a power of 7, which when you increase by 1, it becomes 8. There's nothing about the 1 because, see, you had a prime factor whose power was 0. And that is why when you increase it by 1, it becomes 1. So having a power of 0 is as good as not having a prime factor. So this is possibility 2. Possibility 3 now is this one here. You had a power of 3 on the first one, so 3 plus 1, 4, and a power of 1 on the second one, so 1 plus 1, 2. Now you see there are 3 possibilities for the prime factorization of x. And how can I understand this? How can I relate this with what I want? I want really the prime factors of k squared times x to the power n, not just x. But again, we know this. We just learned this. First point, k squared times x to the power n will have the same prime factors as kx. Why? Because powers do not affect prime factors. And then kx and x. If you remember the rule, everything depended on this k, whether it was already a part of x or not. Now here you are given this information that k is a factor of x. So k is already a part of x, which means k is not contributing to anything else. It's not giving you any other prime factor. So kx will have the same prime factors as x. Now, how has this really simplified my question? I was looking for prime factors of this thing, this mess here, k squared times x to the power n, but now I know it's really nothing but the prime factors of just x. This is what I'll focus my energy on. And I already know 3 possible prime factorizations. This first one, I had 3 prime factors, p1, p2, p3. Second, just 1 prime factor. Third possibility, 2 prime factors. So I don't know how many prime factors x will really have ultimately. After analyzing everything, there are still these 3 possibilities. So when you see the options, you want to know, okay, how many prime factors does it have? This will be, cannot be determined. You can't really tell. I have this comment by Nikhil. Please give a real example for 8 times 1. Well, just see any prime number. You have, say, 2 to the power 7. Then 2 to the power 7 is x. You want to know how many factors it has. You just increase 7 by 1. It's 7 plus 1, 8. Essentially, having 8 times 1 is like not having it at all. We just wanted to show how 8 can be expressed as a product of numbers. Had I just written 8 equal to 8, you would have thought, yeah, that is obvious. Where is the product? That is why we've written it as 8 times 1. But whenever it's a times 1, that prime factor really does not exist. So this is the solution for the third question. Accuracy was 56. Again, 44% of you who got this wrong. I hope everything is clear. If not, please comment here while I talk about the takeaways that we have from this print. First point we really worked on was this, that k to the power a has the same prime factors for k. So powers do not make a difference for positive integers, k and k to the power a. Remember, both of them had to be integers. Here, a need not be an integer itself. So this is something which people usually just assume that you can't raise it to any other power. You saw a question where we had square root of q. Now, just because square root of q was an integer itself, we could apply this result. Otherwise, if you would have thought that, okay, a has to be an integer, then you would have rejected square root of q. You would have thought, okay, the power is 1 by 2, so I can't use this result. So there is a faltering point. Second, we saw this, that Ka, when you multiply, it may or may not have the same prime factors. This depends on the prime factors of K and A, whether A is already a part of K or not. Third point we saw was this. This was something I've been talking about since the beginning. Prime factors and factors are different things. Prime factors are the building blocks. They're just what make the number up. Factors themselves are created using prime factors. So when I had the number 10, my prime factors were 2 and 5. And then my factor was 10, which is just 2 times 5. So there's a difference between the two, and that's why we calculate them differently as well. This was sprint 1. I see no questions in the comment box, so I think everybody is very clear with this. Let me talk about this next very important thing where you can get many more questions such as these. We have till now done 7 questions. You will find, I don't know how many, 70 or more on this platform. This is Quant 2.0 trial. It's our new offering in the Quant course. Based on this expert ideology, you personalize, engage, reinforce, and track your performance all at the same time. You will be able to understand where you're starting from. You will be given a diagnostic quiz topic wise. So every topic you will know where you stand. Then it's an adaptive course. It will guide you what to do, what not to do based on your diagnostic. If you perform really well, it will tell you which concepts to just skip, that okay, you know this thing. You can of course do them at your own will, but it's a very adaptive and very full of feedback program, Quant course. So make sure you access this, try to access this. It is in the link to this is in the chat box. Atreya just posted it. We have this focus on process skills in the entire Quant 2.0 project. Process skills are what really? Just think about this. Have you ever faced this, that I know a concept, but when the question comes in front of me, I don't know what to do? Why does that happen? Why is there a gap between concepts and application? Well, that gap is what process skills will bridge. It will tell you how to go from what you know, from your conceptual understanding, to applying them on concepts. We have these 6 process skills: infer, translate, simplify. I will not just take the names because you will really need reference to understand them. And for this, you can get some free video lessons. The link for those lessons is again in the chat box. Access this, make this a part of your quant preparation, and see the change. After all of this discussion, we are all ready for sprint 2. This, as you know, is going to be the 700 plus level questions. Here you have the instructions. 2 questions in the next slides, 700 plus. Again, polls are the only place we will put our answers in. Every question will be solved the moment you attempt it. These are going to be data sufficiency questions, so just brace yourself for it. Don't be intimidated by DS. Apply everything you've learned till now, step by step. Here we will get the link for the question soon. This is question number 1. Let's start. Good luck. All right, let's discuss this. We have the accuracy. It's 57% of you got this correct. So again, it's in the 50s. Let's discuss this, and please do tell me what is it that is still confusing, if anything at all, because we're coming towards the end of the session. I want to understand how you've received everything, what things are still stuck in your mind. This was the question you attempted. Let us discuss this. Here's what you have. How many prime factors does Q have? Square root of Q have. Okay. So if I want, we already dealt with square root of Q earlier, and we saw how square root of Q will have the same prime factors as Q, just if we know that square root of Q is also an integer. So keep that in mind, all the learnings that we had from our previous questions. With that, if we analyze statement number 1, we see q to the power 8 has 3 prime factors. Okay, then I can say q has 3 prime factors because q and q to the power 8 are both integers and powers make no difference. And if q has 3 prime factors, I can say square root of q has 3 prime factors. Can I say this again? Remember, I just told you that we have to make sure that square root of q is an integer. So right now, this first statement alone gives us no information about that. So we cannot conclude this unless square root of q is an integer. So this will only happen if q is a perfect square. So if q is the square of something, then square root of q is automatically an integer. But statement 1 does not tell us that, and therefore statement 1 is insufficient. Next, let's see statement 2, and we're keeping this here so that we don't miss this again. Statement 2 tells us that q is the square of an odd positive integer. So that means q can be written as n squared, where n is an odd positive integer. It just had to be a square. Then if q is n squared, then square root of q is n. So we are done with this part that we're looking for, whether square root of q is an integer or not. We found that out. But does this tell us how many prime factors square root of q has? Okay, I can now conclude that prime factors of square root of q are the same as prime factors of q, but where do I know anything about q? I don't. So I need to know the prime factors of q and then relate them to square root of q. So statement 2 alone again does not tell me that. So statement 2 is not sufficient alone. What do you do next in a data sufficiency question? If statement 1 fails, statement 2 fails, then you bring them together. You think, okay, alone you can't help me answer this. Can you help me answer this together? So these two now come together, statements 1 and 2. Statement 1 gave us what again? That square root of q will have 3 prime factors, but the only condition we had there was only if q is a perfect square. So we were missing that piece of information there, and that is why we could not straight away just give 3 as our answer. But statement 2 now tells us that q is a perfect square. Essentially, the only piece that we were missing, statement 2 has given us that piece. Whatever was missing is now there. So you can combine these two together to say that square root of q does have 3 prime factors. And so whatever you were looking for how many prime factors it has, you got the answer when you combined the statements. And in a data sufficiency question, when two statements are sufficient together, the correct answer, the correct choice is choice C. Here is question 2 now. We will have the link there. Let's talk about 2 and come to the feedback after that. There's the link. Okay, I see Sumit is posting here. Well, the accuracy this time is surprising. We have 6% of you who answered this correctly. So 94% of the people got this wrong. I'm going to go slow with this one now. I want everybody to understand this, and I want a little more participation in the comments now. I want to understand what is it that is confusing, if at all. I'm going to go slow with this. So here's the question, and let's see. K is a positive integer greater than 1. How many prime factors does 14k have? Remember, bit by bit, piece by piece, do not get overwhelmed. So, before I even read the statements, I'll only focus on the question stem. This is the stem of the question. This first piece just tells me it's something greater than 1. So, 2, 3, 4, 5, it could be anything. Then this second part says how many prime factors does 14k have? Okay, so I want something about k and 14. So although I have no idea about k, I know what 14 is. I know what 14 is made up of, right? So let's understand that a little more. Let's dissect that a little more. 14k, now there 14k can be written as 2 times 7 times k, because 14 is 2 times 7. Now, the possibilities that I want to analyze here are whether 2 and 7 are a part of K or not. Why am I thinking about this? We already know this. We know when you consider K and AK, then what you really care about is whether A is a part of K or not. So this is what affects the prime factor. So here also I want to see what about 2 and 7 and K. So there are multiple possibilities here. First possibility is that 2 and 7, both of them are factors of K. That's possibility one. Situation two is that just one of them, just 2 or just 7, they're factors of K. And the last situation is that none of them, neither 2 nor 7, is a factor of K. Now, how does this affect what I'm looking for? Just be very careful here. Remember, you want to look for the prime factors of 14k, and you want to connect them with just k. How do I do that? What do I do? Look at this first piece. I've made a statement here. It says prime factors of 14k are equal to the prime factors of k. Why am I saying this? Think about this. You have k, this is k with all of its prime factors within it. Now, 2 and 7 are already factors of k, so they're already within this. So, if I give it an extra 2 or an extra 7 because of 14, am I changing the number of prime factors? No, I'm giving it what it already had. So, nothing is going to change. So, in the first situation, it's just going to be prime factors of k. Let's see how this is different in statement 2, in situation 2. So, this is what I'm saying. See why. Again, think about it. I said only one of 2 and 7. So suppose just 2 is a factor of k. So this is again my k with all of its prime factors, and you have 2 within this. But when you bring in a 14, you bring in 2 and a 7. While the 2 is already within this, I don't care about this, but the 7 is one new factor that this is getting. Therefore, if I'm talking about the prime factors of 14k, then I have everything from k, yes, but one more. Just that 7, basically. You have one more. And in the last possibility, if none of them is a factor, what's happening is all of this is k, you give it 2, you give it 7, it gets 2 new factors, 2 new prime factors. So 14k as a whole has 2 factors plus the all of those from k. So that is why I'm adding 2 here. This piece, first of all, should be very clear before we move on and see anything else. So, anything about this? Anybody wants to say anything here before I move on? Anshul says she chose B, but maybe I understood statement B differently. Okay, the question statement, are we all on the same page for this? I will move on, but I want all of you to be a little more interactive here. Now, statement 1 is what? Statement 1 is that k to the power 4 is divisible by 100. Okay, let's see what this means. K to the power 4 by 100, but what is 100? 100 is just 2 squared times 5 squared. So what this means is that k to the power 4 is divisible by 2 squared times 5 squared. So these are the factors, the prime factors of k to the power 4. So this is how I'll say this in a simpler statement, that k to the power 4 has 2 and 5 as prime factors. Okay. Now again, you know one thing. You know that k to the power a and k have the same prime factors, right? So if k to the power 4 had 2 and 5, then k also has them. So this is really what I get from statement 1. K has 2 and 5 as prime factors. At this stage, can you say anything about any other prime factor? Can you say that k does not have a 3 or that k definitely has a 7? You cannot. We get no information from statement 1 about this. This is all you know. It has 2 and 5. Nothing else. I don't know anything else about that. So it may or may not have other prime factors, as I said. Now remember, everything here depended on what k has, whether it has 2 and 7 both, just 2 and 7, or none of them. Here I know one thing. I know 2 is definitely one of the prime factors, right? So if 2 is definitely one of them, then this none case is out of the picture, right? But I can still have this situation. I can either have 2 and 7, or I'll just have 2. Do I know anything about that? I don't. So statement 1 is still insufficient because we don't know between these two cases. So if anybody marked A or did not know how to analyze this, this is all you had to do. And make sure you understand that we have applied nothing besides everything that we've discussed. Not one piece has come from this outside the stuff that I've already talked about. It's all about being patient and going slow with these. These are hard questions. You can take time. You're allowed to take time. Not too much, of course, but when you're learning, that should be okay. Now that we've rejected statement 1, let's look at statement 2. Okay, we have a clean slate now. Statement 2 tells us 50k has two different prime factors. Okay, so I already have 50 here as a participant and I have k as well. And this product together has two different prime factors. Now look here, 50 is what? 50 is 2 times 25, which is 5 squared. 50 already has two different prime factors. That means when I multiply 50 with k, I'm really not getting anything new. So k is cannot have a 7 or a 3 or an 11, because then my number of prime factors would not have remained just 2. So I can make a statement here that k has no prime factors other than 2 and 5. I don't know whether it even has these, but nothing other than this. Now, with this, you move on and you conclude that k may have only 2, only 5, or both 2 and 5. Again, you're not clear. Rahul says he assumed 50k as k has 2 and 5. Okay, so you assume that it definitely has 2 and 5, but the way we understood this right now, it's nothing other than 2 and 5. We are not sure about 2 and 5 themselves, but nothing outside these two. Now, what do I do with this information? Does this help me answer? Does this not? Well, there are a lot of questions. Let's see this one by one. Suppose this was the situation that k has only a 2 and not the 5. Then both none of 2 and 7 is a factor. This case will again be out. You will definitely have this. Why? Because you know you don't have a 7. How do you know that? Because you know you have nothing else, nothing other than 2 and 5. So 2 and having 2 and not a 7 is the only choice. You can't even have this, both 2 and 7. Why? Because we know we have nothing else. So if you do this, k may not have even 2 and 5. Yes, so there may be a situation that it has none of those. Now here, I've only considered this one possibility where k had a 2 and I got this one situation. But what if k has only the 5? Then I will be in this case, right? Sorry, in this case where it's none of 2 and 5. So I'm still not sure which one it's going to be. There is still a lot of confusion. I'm not sure which case it is. And so statement 2 is also not sufficient. What do you do again? Both of them have failed individually. Bring them together. Let's see. Statements 1 and 2 together. Statement 1 told us K has 2 and 5 for sure. It could have extra stuff. So let me make this like this. Let's make this interesting. So this is a box. This is K. It can have a lot of stuff, but it definitely has 2 and 5. It may have other stuff. This is what statement 1 is telling me. Then statement 2 says K has no prime factors other than 2 and 5. So, whatever I was thinking, it may have other stuff, that is now rejected because of statement 2. It's saying it can't have anything else. So, when I take this together, you see your box just has 2 and 5. So, it's super clear that you cannot have anything else and you will have these. So, K has just 2 and 5. So, you now clearly know the prime factors of K, and that is what you were looking for. You're looking for what K is. Now that you know what K is, you'll know which case out of these it is. And once you figure out which case exactly it is, you will be able to get your answer. Let's see which case it is right now. It is only 2. And you see that matches with this second situation here, where you had only one of 2 and 7, right? So here's the 2 you have. And therefore, since you're in this case, prime factors of 14K are going to be 1 plus prime factors of K. And prime factors of K are how many now? 2, 2 and 5. So your final answer will be 3. Not that you want the answer in a data sufficiency question. You just want to see whether you can get it or not. So the answer here is option C. Again, they are sufficient together. I hope this is now absolutely clear. Given the low accuracy that we had on this, I took quite a while on this. Please tell me if there's any confusion. Thank you, Manita. Anybody who has any confusion in this, let's see some comments. Why K has no other factor than 2 and 5? Well, that is what statement 2 told us. No, because 50K has 2 prime factors and 50 alone had 2 prime factors. So K can't be contributing any new prime factor, because otherwise the number of prime factors might become 3 or 4 or so on. Rahul says from statement 2, we cannot say K does not have 2 and 5. Statement 2 was just saying that 50 with K has 2 prime factors. How does that tell you anything about K? Just take possibilities. Say K is 1. Then 50 times 1 will have 2 prime factors. Say K is 2. Then I also 50 times K will have 2 prime factors. Say K is 5 or K is 10. In all of these situations, statement 2 is going to be satisfied. We can't say anything. So it has to be just 2, just 5, both 2 and 5, or none of them. K can be 1. But, okay, sorry, this question says it's greater than 1. So this situation is out. So it's either just 2, just 5, or both. Yes, Rahul, as you pointed out, that is perfect. Thank you, Sumit. I hope everybody now is super clear with this. This was the end of sprint 2. And the takeaways we have from this are these. You have to thoroughly analyze every piece of information. Do not get overwhelmed by the detail in a question. Take it bit by bit. Think about driving in the fog. You can't see where you're going, but you can see the very next, the part of the road. Just think about that. Go slow, trust yourself, trust the concepts, and apply them carefully. Now, you have to use your conceptual understanding and infer as much as you can. So don't just move on from one piece of information to the next. Okay, I've read this and I'm done. No. Think about everything you can conclude from it. So when I read a certain thing, I read K to the power 8 has 2 prime factors. I will say, okay, then K has 2 prime factors. This is where I'll end. This means I have understood my statement. I've done whatever I could with it, and now I'm going on. So essentially, don't be stressed. If you're if it's less stress, then it's more confidence. If it's more confidence, then it's higher accuracy. It's all connected, and less stress just means don't read the whole thing at once. Read a piece so that it doesn't scare you. Don't stress yourself with this. Now, again, I will just tell you about the Quant 2.0 trial one more time. Remember, you have a lot more of these questions that you can practice from. We could just do 9. How many do we do? Yeah, 9 together, but there are many, many more. practice this, get comfortable with the concepts. Quant 2.0, the link is there in the comment box. And the upcoming webinars, make sure you register for them. You'll learn more great techniques there, strategies there. RC webinar on Saturday, 6th February, 7 a.m. PST, 8:30 p.m. IST, and then an algebra webinar, 7th Feb, the next day, Sunday, same time, 8:30 p.m. IST or 7 a.m. PST. And the personalized study plan, you make sure you book your call. This will give you a very good starting point if you're still starting, or if you're stuck somewhere on the way and you don't know how to make progress. We're there to help you. Our experts will help you. And process skills, make sure you watch the videos on process skills. You will see how everything becomes so easy. Now, really, the last question that we did, which had just 6% accuracy, why did that happen? All of us knew the concepts, right? I told the concepts to everybody. But why did that not happen so comfortably? We probably were not inferring stuff. We were not taking out meaning from things as much as we could have. We were not translating things from all that English to a mathematical form. We were not simplifying information. These skills, they're just they're the core skills that have to be a part of the way you solve a question. So watch the videos. The link is in the comment box. You will see how each of these has such an important role in solving GMAT questions. As next steps, now that I'm signing off, I'll tell you what you should be doing. Go through the free videos, the free trial videos and practice quizzes. Practice your hand and get comfortable with the concepts. Then prepare for the webinar on Sunday. If you watch the free videos and are prepared in advance, you can understand more in what happens in the session. You will be able to ask the right kind of questions instead of when you know nothing about a thing. And solve Scholaranium quizzes on the website. So Scholaranium is our platform where we have a lot of questions. So you would be tired, but the questions would not end. They are great GMAT level questions, perfect GMAT style questions, nothing here and there. Solve them, get comfortable with everything. I would now say thank you for attending the session. We had great participation today. And please post your feedback on the feedback form that is now in the chat box. Thank you for attending.